Now, this is the last day. This semester, but could not have been soon enough. So, any particular questions on the practice test? Yes.
Oh, on practice test, like on the homework.
Oh, well, I'll take that too.
Okay. On section 15.8, number 8.
Okay.
There's no example, and I'm not exactly sure about how to go about solving it because I could find the integral or the function, I should say, but I couldn't figure out the boundaries.
Okay, that's number 8.
Yes.
Okay.
It's divergence theorem 1.
Yeah.
Well, they're all basically.
Oh yeah, that's this section. I should add the I just wired this into MyLabs Plus, and there are 20 homeworks altogether. The lowest homework gets dropped. And
why am I doing this?
okay. So well, now that becomes an interesting question now. Okay. But yeah, if you have any particular low homework grades, but now MyLabs Plus is dropping your lowest that you have so far among the ones whose deadlines have passed.
It's already dropped it.
Right. So it's not like an extra bonus. Okay. Number 8. Okay. So region. Okay. All right. So it's asking for the flux across the region D. So, okay, yeah, this is an interesting one indeed. So, D is the region between two spheres. So, in my version of a problem, the sphere of radius 4, I'll use rho equals 4 for spherical coordinates, and then the outer sphere is of radius 5. And it's asking for the flux of F. So if I define S is equal to S1 union S2, where S1 is the outer sphere and S2 is the inner sphere, a flux of a vector field F from this surface, both surfaces taken into account, by the divergence theorem is the integral over the interior of the divergence of F. And your F in this problem is, 4z plus 5x, x minus 9y, 5y plus z. Okay. Well, first of all, what would the divergence of this be? If I label these as P, Q, and R, but by the definition of divergence, Px plus Qy plus Rz. So what would that be in this case?
It'd be 5, negative 9, and 1.
5 minus 9 plus 1, so it's equal to minus 3. So what you end up getting is, so you get, so the integral of this divergence is minus 3 times, well, you can look at it 2 ways. This is the integral of 1. But the integral of 1, a triple integral of 1, is what?
That's volume.
What?
It's volume.
Volume, yeah. So length in 1D, area in 2D, volume in 3D. So in fact, if you were to actually evaluate the integral, just to use spherical coordinates. Okay, I forgot the minus 3. So then we have, what's the extra factor for spherical?
It's like p squared sine theta.
Yep. Not theta.
5.
Unless you're a physics student, then it's theta. Because they have to do things differently. D, rho, D, by d theta. Well, what's rho in this case? What are the limits on rho? 4 to 5, yeah. And then for phi? 0 to pi, because you're going all the way from the North Pole to the South Pole. It's not like a lot of problems where you have to only the top half. And then theta will be 0 to 2 pi. So then you can split this up into one integral of d theta, another d phi, another d rho. But in fact, you don't need to do any of that in this problem because you know the formula for the volume of a sphere. And you can just subtract. So volume of a sphere of radius 5 minus the volume of a sphere of radius 4, and then don't forget to multiply by the minus 3, and then you're done. So that's something to keep in mind, because some problems for Galicus where it boils down to, this is just an area or a volume of some shape, a familiar shape, and if you could use the volume or area formula for that, go ahead. I'm not going to know. Well, for the homework, I won't know or care. And for the test, I honestly think that's a good thing. If you recognize that, if you recognize it easier way. And I know it's going to sound incredibly false to you, but mathematicians really are looking for ways to solve our problems more easily, not less. So it's just that the problems that we have are pretty dang hard. So, okay. Are there any questions about the setup of this one? Or any practice test problems? Number 7. Okay. All right, so that's going to be... yeah, a good old change of variable. I know that caused people a lot of fits back then, around test 2. Okay. Okay, so we've given a change of variables, x minus y, these x plus y, and okay, so this is your original double integral, and r is a tilted square. So we have 1, 2, 2, 1, 3. So this is r. So a change of variable of u and v is basically a way to rotate the square so that it's aligned with the x and y axes. So you can have integral of constant limits, because you didn't just break this up into 2 integrals. Have variable limits for for a dy. Okay, so what you need to do is now. At least the integrand itself is easily transformed, because we're going to have u over v, and then you have your Jacobian, du dv, but then the limits have yet to be determined. Okay, now, as far as the Jacobian is concerned, you need to express x and y in terms of u and v instead of the other way around. So it's important to invert the relationships that you have. So for instance, you can say x is equal to u plus y, and substitute that in here to get v is equal to u plus 2y, and then solve for y. So y is going to be v minus u over 2. And then you can substitute that back in here and get x is equal to u plus v over 2. So this is something you can expect them to do. The particular algebra you use may be different. For example, on test 2, the way it needed to be done was, instead of working with linear equations, you had working with square roots and such. But the point is, elimination and substitution of some kind to go from having these kind of equations to these kind of equations. Okay, old variables in terms of new versus the other way around. Once you have that, that feeds directly into your Jacobian. So if you're not given these relationships at the start, you need to get them. Now, your Jacobian, so that formula we get on the formula sheet, so it's xuyv minus xvyU. So you would use these formulas to compute all the partial derivatives, and at least they're linear functions, and what you end up getting is 1/2. But I have a hunch that it's the other part of a problem that you're asking me about, not the Jacobian or the integrand, but what to do with the limits, right? Yeah, that's the hardest part of this problem. But first, any questions about these steps? Now, because the question is, the whole goal of this is to get some new square, which I'll call r tilde, but what are the dimensions of that square? And the way you can get that is, for shapes like these, get the equations of the edges. So here we're given, this is a point, x is 0, y is 2. This is 1 and 3. This is 2 and 2, and this is 1 and 1. Now, this edge, you can see it as a positive slope. We have it's a slope of 1. And in fact, actually, I'm going to blow this up so you can see it better. Okay. The equation of this edge, and you can get this information from the points, because all these are given. This is y is equal to x plus 2. Notice these points, y coordinate is equal to the x coordinate. That tells you the equation of this edge is y equals x. Now, I can rewrite these. I can say x minus y is equal to 0. I can say x minus y here is equal to minus 2. But what is x minus y also equal to that's written on this board? U. These are my u limits. So my new integral, or du, I'm going to have from minus 2 to 0. So those will be limits for my u variable. And then for the other edges, like for instance, this edge has a slope of minus 1. So this is y is equal to minus x plus 2. And this one's going to have y is equal to, because you could extrapolate to get the y-intercept, it's going to be minus x plus 4. So from the other two edges, you get y plus x, which is v, is equal to 2, and y plus x is equal to 4. So those are my limits in v. So, all right, so if I were to highlight important points to remember on how to do these things, the things you don't find on a formula sheet, because that's what I'm really testing you on. This is huge. Elimination, substitution to express the variables in the form that you need them. Second big point is get equations for the boundary of your original domain, if they're not already given. In some cases, they are. Now, I mean, it's always given in some form. It's just not the form you really need. Here, the boundary was described in terms of these vertices, but you needed to get that in this kind of form. We have equations in x and y to get you your limits. If you look at other problems, like other examples I've done, or like practice test problems, related to change of variables, that's a pattern. It always works that way, that if you get equations that describe the boundary of your region, then what happens is the type of function of x and y that you have, like y plus x in this case, x minus y in this case, those are used to determine formulas for u and v. Why? Because this region is defined by y plus x is equal to a constant, or x minus y is equal to a constant. So that way you and the reason for that is, what do we want? Constant limits. That's what makes integrals easier. So if you can express your original boundary in terms of an equation of form function of x and y equals constant, then your new variable will have constant limits. So look at any example or test problem we've seen where there's some general change of variables like this, and you can pick out these two steps were always done, or something was given so that you didn't have to do it. I mean, one of the difficulties of problems like this is it's only possible to. It's not possible to give a recipe or an algorithm for each type of problem. Books or instructors can only go so far, but what we can give you is a framework, and this is that framework. Is there any questions about this one? Okay. All right, so equations of a boundary give you your limits. Any other problems from the test? Y'all just want a cake. Okay, actually I'm not surprised that that one will be asked about. Okay, and to look at 8. Line integral. Okay. I was thinking about 5 weeks or so, I'll be back in this room seeing a number of you and many more polymer science students for DE.
Yeah, that's what I thought too.
What? Oh God. Okay. No, that's reserved. That privilege is reserved for other classes like modern or real analysis. No. Okay. Something for math majors to look forward to. All right. So the given line integral is a square root of xy dx plus e to the y dy plus xz dz, and the curve C is given by these parametric equations: t to the fourth, t squared, t cubed. T goes from 0 to 1. Okay. Now, is there a particular part of this one that posed difficulty? Or?
The entire thing.
Okay. Well, that's good. All right. Okay. So we're substituting. Okay. So this is your x. This is your y. This is your z. So that means that dx and dy dz. So this is something that should be like a reflex for these kind of problems of line integrals. You get these parametric equations, you need a derivative of all of these. So dx is going to be 4t cubed dt, dy dy is
2d
2d dt, and dz is
3t squared.
3t squared. So now we can substitute all of these throughout. So we have square root of x times y, then dx, but that's going to be 4t cubed dt. And then we have, well, actually, I don't have to write the dt here. I'll have a dt at the end. Okay, so this is square root of xy dx. And e to the y, that's e to the, that's a weird plus sign, e to the t squared, and then dy is 2t dt, plus xz, so that's going to be t to the fourth, t cubed, and then dz is 3t squared, and then we have a dt at the end. Okay. And now a boatload of simplifying to do. Well, from 0 to 1, because those are the given limits on t. So what do we have? T to the 4 times t squared is t to the 6. Square root of t to the 6 is t cubed. So we're going to have times 4t cubed. So that's going to be 4t to the 6 for the first term. And then you have, okay, 2t e to the t squared for the second term. And then we have 3t to the 9th, adding the exponents, not multiplying them. Okay. All right, questions to this point?
Okay, yeah, I got it.
Okay.
I was just having issues with the substitution.
Oh, okay.
Yeah, I was just confused.
Yeah, and the thing is, for going from here, the first two terms, of course, are straight power rule. We don't need to talk about those. But this one, how do you handle that term? That's a little different. U substitution, and what should u be equal to? T squared, and then du is 2t dt. Now, keep in mind, it's very common that this happens. That happens in several examples where you have multiple terms like this and you handle them differently. Most careful thing to do is just break them up into separate integrals. Like in this case, I would say, since you're going to handle the first and last terms the same way. All right, so this is one integral you handle by straight power rule, and then the other one's going to be integral of u du after you do the u substitution. And if you plug in t equal to 0 and 1, of course u is also going to be 0 and 1. So then you can work those integrals out, because I've seen it happen where you have several terms and one of them requires a substitution, and for some strange reason they use a substitution on the rest of the terms too, and they make a mistake, and it just gets ugly. Okay. And while when I teach Cal 2, I am known for making integrals that can be nightmares, because Cal 2 is where you learn about these techniques, and because some physics professors bragged that they could handle integrals better than mathematicians, and I had to silence them. And I did, but that's not what this class is about. So, all right. So, any questions on this one? Oh, we're good on time. So, do we have any more from practice test? Okay. Now, actually, I want to make. I have been taking note of attendance, and I see a few more people have shot up. So, okay, make sure I'm not missing anybody. Okay. All right. So this is a tradition going back to 2010 when I first taught this class, that we celebrate the end of the calculus sequence. Okay, I'll get my... So, as you guys are counting down, I will remain here, of course, through the end of class time. So if anyone else has questions they want to ask me individually about the final, of course they can do that. Okay. And this cake comes from Jody's Bakery on Highway 49. And
It's the best cake, like Iceberg.
yeah. And before people start cutting into it, you might want to get a picture, as some students have done in the past. Okay. And this cake is supposed to serve, I think, 35 people, so we should be good.
It's shaped like a pie.
Okay. Okay.
I want a picture.
Well, I guess before you all come up here, I'll get a picture myself.
No more calculus.
Haha.
Dr. Landers, can I get like one of you holding it, please?
Okay.
Please.
All right.
Like you have to like maybe tilt it, like you know.
Yeah. Carefully. Hold on.
1, 2, 3. Perfect.
Okay.
I'll put it on my Twitter.
For those of you who haven't come up here yet, like, what on earth is in this box? Okay. All right. Go ahead. Well, don't make anyone watching jealous.